In our discussion for enthalpy calculation, we have assumed that a bond dissociation energy, for example, was related to enthalpy of a reaction delta H. Now we're gonna involve some more factors that are contributing to the total free energy of molecule or a product. Involves the enthalpy of a reaction, that means how much heat is being generated or absorbed during, for example, bond dissociation, what we have just finished discussing. So it's not only just enthalpy change, the heat energy that changes in delta H, there is also entropy change. So I want you to just kind of have an overall idea of enthalpy and entropy. So the enthalpy is this portion, enthalpy, that is heat of a reaction, either during the reaction heat could be absorbed or given off. Here it is the entropy factor. So the free total energy is a composition of the heat that's being released or absorbed, also the entropy that will be introduced during the chemical reaction. So when we say entropy, this is a disorder. This is a degree of disorder in the chemical reaction. So whenever you are making a bond or breaking a bond, you are changing entropy, meaning that either you'd be introducing more disorder, or maybe you'd be, during the reaction, you might also gain some level of order. So that measure, it's an energy measure, but it relates to how much disorder is introduced during the reaction. So let me just show you a pictorial example of how we can apply that. Remember, we have discussed about bond dissociation. In the bond dissociation, for example, if we just undergo a hemolysis of that bond, that means a fishhook arrow like this would produce A radical and B radical. That actually is the bond dissociation energy that you should put to break that bond into those free radicals. So in terms of delta H, you have to put energy, right? In the heat of reaction, in this kind of bond breaking, we always need to put energy. So that is the delta H that you need to put into effecting to this reaction. But how about in entropy? What did you do? You have one species as a molecule. You had AB. AB molecule now becomes into different number of items. A by itself, from each 1 mole of AB, you are creating 1 mole of A and 1 mole of B. What you have done is you increase the disorder. In the reaction vessel, you have A species, B species, other species, so you actually created more disorder. In that case, your delta S is greater than 0. So when you are creating more species by breaking a bond, you are creating more disorder. That means the entropy has increased. Entropy is positive in this case. So you have a positive contribution, you have a positive contribution in this case as well. So I think overall the delta G could be less than 0 or greater than 0 based on how much that difference is. So delta G, the free energy of a reaction, is what actually is a complete understanding or a complete accounting of the energetics of a reaction. It's not only just knowing enthalpy of a reaction like what we have done earlier, but you have to also consider, am I increasing entropy? Am I increasing the disorder during the reaction? So that could be a favorable one, or it would be not a favorable. So, for example, in this case, increasing entropy would actually become a more favorable aspect of the reaction, because you would get a more negative number here, because T is always positive. This is, the change is positive as increasing, therefore you have a larger negative. Therefore, as a result, delta G could become less than 0, therefore favors the breakage of the bond. So that is entropy driven. This reaction would be then entropy driven. So the increasing entropy would drive the reaction. That means if overall delta G becomes less than 0. Okay, if you have X, let's say they were this much far apart, but when you react this species, when you put it into a reaction system, it becomes, instead of stretched out like long chain, if it becomes a tiny cyclic system like that, instead of just the disorder like making it a very long chain spaghetti like structure, it becomes like a small circle. The entropy is now, you are actually decreasing entropy. The disorder is being decreased. So decreasing entropy here means it becomes negative. Negative to negative is, that's positive. Overall, the delta G being greater than 0. So it may not be a very easy reaction to undergo, because it is it's decreasing entropy. So decreasing entropy is not a very easy, natural process to undergo, so that cyclization of X, Y may be highly energy demanding, that means. So this is entropy decreasing reaction type. So if we have also, you have AB like this, and you are creating A plus B plus C species. Now, by reacting A and B, actually AB is this molecule, let's say it decomposes, decomposition of this molecule AB into species like A molecule, B molecule, different type, C molecule, you are increasing the disorder. The disorder is being increased, that means entropy is greater than 0. When entropy is greater than 0, okay, maybe then if you have delta H is less than 0, delta S, if it is greater than 0, you have a favorable situation to decompose it. So the energy of a reaction is a contribution of enthalpy, heat of a reaction, that either you need to put in, or the heat of a reaction that is being given off, plus consider what is the effect in terms of entropy that reaction would produce. Here the entropy is being increased, here entropy is reduced, here entropy is increased. So overall, when we really are trying to investigate reactions, we consider both enthalpy and entropy to calculate free energy. This is called a free energy. Because in a free energy, if free energy as a whole, at the end of the day, if it is less than 0, that reaction is favorable, and it's called exothermic. Actually, it generates extra heat or extra energy. Actually, you can call it exergenic. And if delta G is greater than 0, this is endothermic. It needs external energy. It's not spontaneous to be carried on. So But that delta G is contributed by enthalpy, heat of the reaction, and entropy. So you have to consider, at least for entropy, what is the entropy being in terms of hemolysis, for example. A hemolysis, a bond hemolysis, would produce different radicals like A dot, B dot. It means that you are increasing entropy. It's favoring delta G to be less than 0. And if you cyclize, let me just tell you what the name of this is. This is hemolysis. I think we have covered this hemolysis of a bond. That's the breakage. This is cyclization of a reaction. It's called cyclization. It decreases entropy. This is decomposition, let's say. Decomposition reaction. So if A is decomposed into different species, entropy is greater than 0. So overall, this is just to remind you that a reaction, the energetics of a reaction depends on enthalpy and entropy. Both of them are important. A heat of reaction and the disorder that the reaction would produce in terms of that kind of procedure. Now, I want to tell you some facts. In some cases, in most cases, the contribution of, in organic reactions, the contribution of delta S, the entropy disorder, sometimes it's not, in most reactions, it's not very significant. So delta G, free energy, can be equated to delta H naught, direct free energy, and enthalpy can be equated approximately, because we can assume delta S to be close to 0. In most cases, we can assume this and simplify our calculations or simplify our thinking of a reaction. Sometimes we can just directly equate free energy mean enthalpy of a reaction if we assume the entropy of that reaction is not very significant. So it depends. These are like extreme case of producing more disorder or improving disorder. But there are some reactions where the differences are very subtle. In that case, the entropy change is not that significant. Therefore, I can just assume delta G is the same as delta H, because the entropy contribution might be close to 0. So, as we move along on this subject, the next section would be just to introduce transition states, energy diagrams, schematically, and also I think we would briefly touch on kinetics of a reaction. Here what you see is a thermodynamic equilibrium reaction energies. This is equilibrium. It doesn't tell us when we say delta G for a reaction is it's generally exothermic, that means products are more favorable to be formed. Delta G greater than 0 means product formation is not that favorable, we need to put energy. But it doesn't tell us whether how fast that reaction can happen. For example, this piece of paper, if you just leave it under the sun, this has some glucose in it, it's made of fibers. It could burn in 120 years. That means thermodynamically, delta G is less than 0. But it doesn't mean that it is the same as like lighting it with a flame, which just burn as well. It's the same burning. So how fast a reaction can happen is not governed by this, by free energy. Free energy is just a thermodynamic quantity to tell you whether that reaction is feasible or not, or what that product is stable or unstable. But how fast the reaction would go is determined by other kind of energy like activation energy and etc. So we will discuss those during the transition state discussion and also energy diagram. Hello everyone. Continuing our discussion on the energy of a reaction. As you remember, we just finished by calculating the delta H of the solubilities of terbitanol in water, and we found out that the reaction is exothermic by -3 kilojoules per mole. That tells us the reaction would go forward, favoring product side. In today's discussion, I will be going a little bit deeper and show you some of the chemical equations that are relevant to calculating equilibrium constant, and we also will check on the kinetics of a reaction versus a thermodynamics or equilibrium situation in a reaction. So the delta G, free energy, or delta H, the enthalpy of the reaction, delta G is called free energy of a reaction. So I want you to just keep in mind these two equations. These are, as it relates to the free energy, delta G is free energy, delta H is the enthalpy of a reaction, T is the temperature in kelvins, delta S is the entropy of the reaction. Another equation which also relates the free energy to the equilibrium constant here. So these are two important equations when we deal with equilibrium situation. What do I mean when I say a reaction is in equilibrium? A reaction would become to equilibrium when the rate of formation of the products, these are C plus D is a product, and the rate of formation of, in the reverse direction, the rate of A plus B is the same. That reaction, we call it an equilibrium situation. So it has reached, most of the products are being formed, and now it's becoming leveling off. So that's a equilibrium situation. So a K equilibrium, this is a reaction constant, an equilibrium constant, is defined or calculated by the ratio of the products to the ratio of the starting material remaining. So how much product is at that point is formed over how much starting material is remaining in the reaction. That ratio, products over starting material would give you the ratio that is an equilibrium constant. So if the forward direction is favored, that means if more products are formed than what is remaining in your reaction, that K equilibrium obviously would be greater than 1. That means the reaction is favored to the forward direction when K equilibrium is greater than 1. What tells me is that more and more products are formed in relation to the remaining starting material. So that's K equilibrium equals 1 suggested that more products are formed. So in terms of energy, for K equilibrium greater than 1, if you just see what the equilibrium would be, it would be delta G for such a reaction where you have the equilibrium constant is greater than 1, the free energy is less than 1. It's less than 1. What does that mean? If you just look at here, when K equilibrium is greater than 1, the natural log of 1 greater than 1 is a positive value. But T temperature, it's positive. R is the universal gas constant. So in the equation we have a minus here. So it will always be delta G is less than 1. But if the equilibrium constant, what is remaining in the reaction, if it is much higher than what is being formed, that means K equilibrium constant is less than 1 value. In that case, if it is less than 1, if you just plug in a less than 1 value here for the natural log, that would be a negative number. T is always positive. You have R is always positive. A negative number times a negative number would be a positive. So delta G is greater than 0. So reactions where you have a delta G value, a free energy value less than 1, is always it favors the products. That means equilibrium constant is very large, and actually formation of the product is much more favored. But if your equilibrium constant is less than 1, it means that when the free energy is less than 0 also, there is the same meaning. That means the starting material is still remaining in larger quantity than the product that is being formed. So the equilibrium constant tells you how much the magnitude or how much is products are favored to be formed. You can also see it by a free energy. If you have a free energy which is less than 1, meaning that's a negative value, that means the formation of the product is favorable because it would give a larger amount of K equilibrium. So this is the formula I will be dealing with when you are looking at equilibrium situations. So equilibrium is different from a rate of formation of a product. In the rate of formation of a product, for example, you might have a delta G value of less than 1, meaning that equilibrium constant is greater than 1. That means products could be formed. But how fast they will be forming is another issue. That we deal it with kinetics. How is the kinetics of the reaction? How fast is a product being formed? These values wouldn't tell us. These are thermodynamic or equilibrium values. This is for equilibrium situation. It doesn't tell us how fast it is formed. It only tells us in how much quantity they would be forming. But how long, in how long time, that is kinetics. It's a different situation. So we'll deal that with a different set of equations. These are equilibrium equations where a free energy is related to R, which is universal gas constant, temperature, and the equilibrium constant. How fast a reaction would move is another kinetic issue. But how much of the starting material would be converted to product is a thermodynamic or equilibrium situation. From equilibrium equations, we would be able to calculate how much that product is formed. So if the products are formed, always if the products are favored, their energy means it is less than 1. So you can also look at it in terms of enthalpy. Actually, for practical reasons, in most organic reactions, the change in entropy is almost 0, meaning that we can neglect it as close to 0. In that situation, remember that delta G naught, the upper equation, can equate just to the free energy, enthalpy, because we are assuming here delta S entropy change. There are no significant entropy changes in organic reactions. So this is an assumption. If we assume delta S to be 0, free energy and enthalpy of a reaction are equal. So for an exothermic reaction, which is delta H is less than 1, the K equilibrium is greater than 1. So we can similarly just suggest that delta H is also less than 1, delta H is greater than 0, delta G is less than 0. That's it. So here are these two equations where the assumption at entropy close to 0 is both free energy and enthalpy are the same, and also the free energy equilibrium, or delta H for that matter now, can be related to equilibrium constant. So it's very reasonable assumption to say that most of the organic reaction result not in a change of entropy. So the entropy change that comes out of organic reactions is almost negligible. That's why we can assume free energy equals enthalpy. So with this, I will continue by just showing you one equilibrium situation where a chemical like this, what it means, you have this phenyl group. This is a chair form of cyclohexane where you have the phenyl group in axial position. This is phenyl group. The rest are hydrogens. Obviously, you should remember that from our chair bond conformation. So this is an axial position. The phenyl is a bulky group now oriented in axial position. But there is an equilibrium between this and the other chair form. Remember, cyclohexane chair forms always interconvert between one form to the other form, so through a both conformation, because to relieve 1,3 diaxial interaction. So let's see this conversion into, when I draw this into the other chair form of that equilibrium. Now whatever you have an axial position, it will be right here. The phenyl will be in equatorial position. So I will just draw this. So here what happened? So this is an equilibrium. That is, there is an energy that should be expanded from going anaxial to equatorial. So if I just generally ask you, what would be the equilibrium constant for this going from here to here? Would the equilibrium constant less than 0, less than 1, or the equilibrium constant would be greater than 1? So this is a trick question, but not a very tricky. But obviously you remember that the axial position of a very bulky group is not favorable. So the product side, meaning that the right side is more favorable. So the equilibrium constant is the concentration of the equatorial over the axial, right? So from your cyclohexane conformation studies, what we have in previous chapters, we have said that equatorial substituents are much more favorable than the axial ones. Therefore, this K equilibrium is actually greater than 1, which is a situation what you see here. K equilibrium will be greater than 1. That means delta G of this system is less than 0, exothermic, as well as delta H is less than 0. It will be less than 0 as well. Because from our chemical intuition, we know that the equatorial position is a more stable and more favorable conformer than the axial one. So in the forward direction, the equatorial over the axial concentration would be greater than 1, and delta G, delta H, both would be less than 0. So that is the thermodynamics. Actually, I have an actual number. The delta G naught or delta G equilibrium for this is, I will just put it right here, delta G naught actually, which is measured for this, is minus 12.1 kilojoules per mole. So it makes sense. Delta G is less than 0. So if you just plug it into something here, you'd end up seeing K equilibrium to be very, very large. It is, K equilibrium is approximately, it would be, if you just calculate, put the 12.1 kilojoules per mole in this, you have R, and just at room temperature, and calculate for K equilibrium, my number shows me the K equilibrium actually is about 100. So what it means is the equatorial conformer is 100 times more stable than the axial. That means 100 times abundant than the axial conformer. So delta G naught for this is minus 12.1 kilojoules per mole, obviously exothermic. We can call it equal to delta H, because if we assume delta S to be close to 0, both enthalpy and free energy would be the same. So if you plug it into this equation right here and find out what the equilibrium constant is, it will be close to 100. That means the K equilibrium is 100 to 1. That's what the meaning is. If you have 100 population of the equatorial, you have 1 of the axial. That is the distribution, axial versus equatorial. So we'll continue with the next section, details of some calculations we can do, and we'll also see transition energy, energy diagram, and so on in the next section. Okay, one of the methods where pictorially we represent energy diagram of a reaction, or the thermodynamics of a reaction, would be using energy diagrams. Energy diagrams are just a plot of energy, that is the amount of energy, delta H it could be, and more in the x-axis you have the progress of the reaction. So if you have a single step reaction, remember we have outlined by just saying that organic reactions, or for that matter any reaction, can be a single step reaction or a multi-step reaction. That means reactants are transformed to products in one single step, would be represented by such energy diagram. So if you have starting materials before the reaction, if you have A, B reacting with C, you have a certain amount of energy. That is the starting point of the starting materials energy, H. And after some time during the reaction, they go to a high transition state, a high energy transition state. This we call a high energy transition state. But to reach to that transition state, energy has to put in. That is what we call activation energy. EA is an activation energy. So this is how much you need to put for the reaction to start or to reach to a transition state complex. So in any reaction, the kinetics, or how fast that reaction could proceed, depends on the activation energy you have. So the complex, the starting material, would recombine, and as it goes up during the reaction progress, it reaches to a transition state complex. This is called transition state complex. Transition state. The species that would be at that point is a transition state complex. It is a high energy complex, and it has already acquired enough activation energy to reach to a transition state. So the transition state, or the activation energy, is what determines the rate, how fast that reaction could happen. Like I remember I said, for example, if you have just a piece of paper which is full of starch and leave it outside on the sun, the activation energy may not be sufficient enough for the reaction to happen in 100 years. But if you just light it up with a flame, that reaction would just happen in a few minutes, burning of a paper. So burning of a paper, thermodynamically, yes, it is less than zero, delta G is less than zero, but how fast it would happen depends on the activation energy. So for any reaction, whether it's a single step or multi-step, I will discuss that, you need to have the activation energy that is sufficient to bring all of the starting material to an activated complex. So these are called actually transition state complex, sometimes we call them activated complex. This stage, having climbing up the hill to reach to the activated complex, is actually what determines the rate of a reaction. So this is the highest tip in the reaction, in the energy diagram, is the rate determining step. Or we call them RDS. So the highest tip of the energy diagram is what determines how fast the reaction could happen. But overall, whether a reaction goes fast or slow, the overall product's formation or the equilibrium is governed by delta H. So that delta H is enthalpy of products minus enthalpy of starting material, gives you that difference. So that difference, when it is delta H is less than zero, that's an exothermic reaction. But in the energy diagram, if this diagram looks like, for example, like this, where delta H is greater than zero, right? Because the starting material and this products H minus starting materials H is positive, greater than zero. That is endothermic. So for endothermic reactions, this is a curve. It doesn't look like this, but it looks like this, where products are here, starting materials are here. But in exothermic reaction, the delta H is less than zero because the enthalpy of the product is less than the product of the starting materials. So main important points is to remember the activated complex is the highest point where a transition is transition complex is formed. Now here, as you see, the A and B bond starts to weaken, it's being broken, and the C bond is being made. So that's everything is together right there. So once that activated complex is done, now fully the CB bond is fully formed, and the A bond is broken when the reaction completes. So at the activated complex, what you see is a loose breakaway of A from B, but a new bond is being formed between C and B. That is the activated complex. That is the highest energy state. To reach to this activated complex, you always need activation energy. So activation energy is always positive. One thing you have to remember is also EA, activation energy. The activation energy is always greater than 0, meaning that you have to put that amount of energy. Somehow that reaction should be activated from external source. Therefore, activation energy is always greater than 0. So what you see here is a single step reaction, meaning that starting material going to product through transition state. But here I have a picture where you have an intermediate between starting material and products. So we are forming this product BC, but to go through that, to achieve BC product right here, obviously this is an exothermic reaction at the end because the delta H is less than 0. It's not like this one. This is an endothermic picture. So here in the multi-step, at least this is a two-step, the hemolysis or the bond breakage of AB happens first through this much activation energy. That is activation energy. Certain amount of energy has to be put in. So now AB is about to break. Once it breaks, it forms this species. So that we call intermediate. Intermediate. Highly unstable, but relatively stable than the transition state complex. The transition state complex breaks down to give you a relatively stable intermediate until it gets reacted by C. So that is an intermediate. So in a two-step reaction, a starting material would go through transition state complex. The transition state complex would decompose or break away to form an intermediate species. The intermediate species again has to be activated a little bit more to recombine with another species, C. So this A, B recombine with C doesn't happen in just a single step like what we see here. This is a single step reaction, but this one is a multi-step, at least a two-step reaction. So now BC starts to form. That BC, finally a full-fledged bond is being formed right here. All products are formed. All the products are stable now at a very low energy. That's the end of the reaction. So the difference between these two mechanisms, this is a single step reaction. In at least a two-step reaction, you have intermediate, not a transition state complex. Intermediate is relatively stable than the transition state complex. This is transition state complex. Very high energy, and it requires activation energy. So if someone asks you between this activation energy and that much activation energy, or overall in this reaction, which one is the rate determining step, always go to the highest step. The highest step in the energy profile diagram is the rate determining step. So this is the rate determining step. So until you get this much activation energy, the reaction doesn't proceed, or it will be limited. So if, for example, you have the same reaction materials, but somehow having different conditions, if you change the conditions, you might have a reaction which goes through this, produces the same thing. So this is activation energy 2, this much. So if I ask you which reaction, they are producing the same thing, their final delta H is the same, but between this reaction and the dotted line reaction, which one is faster? Obviously, the lowest activation, EA2, is the fastest route. So EA is greater than 0, always they are greater than 0, but between EA1 and EA2, EA2 is less than EA1, so the reaction which is fastest is, this is the fastest reaction, faster reaction, because it requires a very low activation barrier. Similarly, if you have this are done by changing some of the conditions. So we'll just look at a condition where you could have a lower activation energy by using enzymes, so catalysts and all that. So a reaction with a lower activation energy is faster than a reaction which has a higher activation energy. So the rate is determined actually by not delta H. A rate of a reaction is not determined by the thermodynamic enthalpy or by delta H. Rather, speed of a reaction is determined by how much activation energy you require. So now two distinctions. A product is formed or stable or feasible to be formed is governed by the delta H, but in terms of how fast that reaction could happen is governed by the amount of activation energy you need for that particular reaction. So we'll continue to the next section. Okay, our discussion just involved the thermodynamics or activation energy, or overall the rate of a reaction is dependent upon the activation energy. So actually the specific equation for activation energy included in the rate would be defined by ln K, this is a rate constant, not equilibrium constant, equals to A is called frequency factor, minus E, activation energy, universal gas constant, and temperature. So these are the two important equations that you'll be encountering during rate calculations. So, like I said, rate is dependent on the rate constant. This is not equilibrium constant. Small k is equilibrium rate constant is dependent upon two factors. One is concentration of reactants, and temperature. These are the most important factors that determine rate of reaction. So concentration, as you see here, is the concentration of AB, that is the starting material, and the concentration of C, one of the reactants as well. In this equation as well, the rate constant K is also depending upon how much the activation energy is and at what temperature. So these are the two factors that are important in determining rate of a reaction, concentration and temperature. So here we can say there are powers like x and y. X and y are called orders of a reaction. That what it means is what is the factor AB compared to C? Is this increasing the rate of A? Is the concentration of AB? Would it be linear or square or triple? So X and Y can be values of 1, 2, 3 whole numbers. So these are determined by experiment. These are experimental numbers based on the mechanism, experimental values. Say, for example, if the rate of a reaction is when AB is increased by double, if the rate is increased, and if C is concentration is doubled and the reaction is doubled, each one of them have rate order of X is 1 and Y is 1. So they depend equally on the concentrations of A and AB and C. Now, if the order of the reaction is 0, for example, for C, that means the rate depends only on the concentration of AB. For example, this is in a single step reaction. All of the reactants, their concentration is important in the rate determining step because they are involved in the rate determining step. So their concentration is implicated. But if you have, for example, a multi-step like what we have earlier, multi-step, and if it's only dependent on the bond breakage of AB, rate equals K, the concentration of A, B. Because at the rate determining step, it is AB that's just involved. The activation energy to break that bond is the first step. So the intermediate B plus is formed. So it's not, C is not involved until B is being formed. So this is in a single step. For example, if you have this, in this reaction, you have, let's say, A, B, and reacting with C. So the first rate determining step, or the highest activation energy, is the breakage of A, B. This is the transition state. Then once B plus as an intermediate is formed, C comes in and CB is formed, A is released. So in the main high activation energy, only AB is involved. So in the rate law also, that's what you read. You write C will not be included. In the multi-step, only molecules involved in the rate determining step are included in the rate law, are included. Only molecules that are in the rate determining step. So AB is what is involved in the highest energy state. So that's the rate law. Rate equals K A into B. And the next equation also tells you how important the activation energy is. For the rate constant is dependent upon temperature and activation energy. This factor, which is we call A is a frequency factor. frequency factor, meaning that how many molecules are collided at a given, the probability of how many electron or how many molecular species are colliding to make that reaction happen. So that's just a constant for different reaction, different frequency factor is included. So one of the strategies in terms of lowering activation energy in biological system is using enzymes. Enzymes are biological molecules, proteins that are involved in biological reactions which help to lower activation energy. That means when they lower activation energy, the reaction goes faster. So enzymes are catalysts. So enzymes, they are not participating in the bond breaking or bond making, but enzymes are catalysts. They lower activation energy. That means speed up a reaction. So that's the role of enzymes, to lower activation energy so that the reaction goes faster. So with this, we'll be concluding the chapter on reaction kinetics and reaction, organic reactions and energetics. In the next chapter, we'll be looking at alkyl halide and some substitution reaction in detail.